Okay, we're going to get started. Hello, everybody, and welcome to LigoWave's webinar entitled Behind the Lens, Designing a Wireless Surveillance Network. I'm Jason Hintersteiner. I'm Director of the Business Development for LigoWave in the United States. And today we're going to talk about how you design for wireless surveillance. So the topics that we are going to cover today are going to be the typical requirements and constraints that one encounters in a wireless surveillance application. We're going to go through a brief overview of point-to-multipoint technology and how that works. Then we're going to dive into the design parameters. So what are the things in the design that you actually have control over, as well as the tools that you could put into place when you are laying out a point-to-multipoint network for wireless surveillance. As part of that, we'll go through some of the LigoWave products and technologies that are suited and designed for wireless surveillance applications, and we'll leave a bit of time for Q&A at the end. If you have questions, please put them in the question window of your webinar box, and I will go through them at the end of the presentation. So why do you want to do wireless in a video surveillance network? So first off, right, why don't I just do everything wired? And the answer is, of course, running everything wired can be very, very expensive. So when you do things wireless, you have a lot of deployment flexibility. I can put the cameras exactly where I want them to go. I can scale the network very easily without having to worry about trenching cable or running fiber or ripping up streets, especially if I need to do shots over longer distances. It can be very, very efficient in terms of time because it doesn't take very long to actually put up a wireless link and install it, whereas installing cable, if you have to get permits and you have to rip up a lot of things, right? It could be very expensive, both in terms of cost and in terms of time. And then, of course, finally, it's much more cost effective to do wireless versus wired. But you need to be able to do wireless the right way. So let's talk about requirements, which is what the system has to do when you're designing a wireless network. And typically when we talk about requirements for any type of wireless network, we're looking at usage, coverage, and capacity. So in terms of usage, I want to look at what are my camera parameters, how many megapixels, what's the frame rate, what's the compression algorithm that's being used, is it H.264 or something more primitive that's going to take up more bandwidth, what kind of video quality that you know, what the image quality is that you want, and so forth. Because that will drive the amount of bandwidth that you're actually going to be pushing for each camera. You need to look at the camera power requirements. Is it PoE or is it something else? You also want to look at if there are other things on your surveillance network besides cameras that you also want this wireless network to handle, such as access control devices, gate devices, if you're doing any type of Wi-Fi overlay. That also needs to be captured in the usage requirements. We then want to look at coverage, which is what are the areas that actually require surveillance? Where do you need those cameras to look? How many cameras do you need? What are the link distances and what's the RF line of sight? And I'll talk a little bit more about RF line of sight versus visual line of sight later on. I also want to look at what are the expected climate and weather conditions, because that will come into a factor in terms of what kind of access point do I pick and what kind of outdoor weather rating is it going to need. And that will depend very much on the environment where it's going. I need to look at capacity. So how many cameras, how many devices are going on this network, and how much data needs to be passed over the network. It doesn't just stop there, because I also have to look at control and integration requirements. So for control, things I mean by control is how easy is it going to be to set up and configure this network, and how easy is it going to be to maintain the network, right? Typically, we're not just going in and throwing up a network and then forgetting about it, right? We want to actually monitor it to make sure that it's operating over time, which means that I need some type of centralized monitoring and management in order to make sure that not only are my cameras up, but all of the wireless links that are supporting them are also online and working correctly. Also, there may be requirements on certain types of diagnostic tools that you need in case there are issues down the road. So you'll probably have requirements on uptime and availability in terms of the, you know, how often the system is up versus down. And hence, that's going to drive the need for certain types of diagnostic tools so that if there is an issue, it can get resolved quickly. Finally, you have integration requirements such as things of ease of installation and maintenance. How easy is it to install the cameras? How easy is it to install the wireless access points to do the wireless surveillance? what kind of lifetime is expected out of the hardware, how long is that network going to be in place before it is likely to be replaced, and what kind of hardware reliability do you expect? And all of those requirements need to be captured up front before you actually start thinking about picking hardware and figuring out where you're putting things. We also need to look at constraints when we're doing any type of network. And if requirements are what the system has to do, then constraints are what the system has to work around. So for instance, I generally just can't put cameras and wireless links willy-nilly anywhere that I want. I'm limited in terms of where I can put these things. You know, if it's an outdoor deployment, you know, do I have access to streetlight poles? Are they public utility poles? Are they owned by the property? Do I have to put the cameras on the sides of buildings? Do I need to do kind of satellite mounts or non-roof penetrating mounts and so forth? And a lot of that will be dictated by the limitations of where you can mount things and where you can get power for these applications, right? So if I need to erect a pole, right, even if I'm using wireless link to connect the data, I still have to get power there. So is there power already available because there's a light available there or some other electrical source I can tap into? Or do you need to put in something like a solar panel array so that you have solar batteries to power that camera and that wireless link? So you need to understand what your constraints are in terms of where you can mount things and where you can get power. You may lack line of sight to all of your locations. So very rarely do I actually just have straight line of sight from wherever your network video recorder is going to be to everywhere where I want to put a camera, and I will be showing examples of that. So typically you need to design in terms of relay shots. So I've got to shoot from point A to point B, and then I might need to change direction and go from point B to point C, and then I might need to go change direction again and go from point C to point D, and so forth. That will typically drive the need for multiple antenna options, both internally and externally. And so the platform that you pick, you're going to want to make sure has support for multiple types of antenna options. Budget is always a constraint. Wireless surveillance, right? People typically want to put in as many cameras as they can and as many links as they can for as little money as they can get away with. So budget is often a constraint. You may have interference from external sources, such as surrounding Wi-Fi. So if you're putting surveillance in a garden-style apartment complex, which is a very common application, those apartments are likely to have their own Wi-Fi routers, which are going to be blasting 2.4 gigahertz and 5 gigahertz Wi-Fi all over the place, and those could potentially interfere with your wireless links. So you need to account for that in your design. And finally, scope creep. I have yet to work on a surveillance project where integrators are not adding cameras late in the game, and sometimes even after the wireless network is installed, the property is still adding cameras. So you need to understand how your scope is likely to creep and build in a certain amount of slack, if you will, right, a certain amount of margin into your designs to make sure that somebody adding, you know, 1 or 2 additional cameras here and there is not going to break your network. So let's talk a little bit about wireless backhaul, and this is typically called bridge mode. And in its simplest sense, bridge mode is connecting 2 or more wired networks together wirelessly. And when we're operating in bridge mode, that means that all of the layer 2 Ethernet traffic gets encapsulated in a wireless link, and such, from the perspective of both sides of the network, it looks like you have a wire connecting them, when in reality, you have a wireless link. And what's happening here is basically I have an Ethernet frame, say, coming from the camera, right? It's coming out its Ethernet port, so it's a standard layer 2 Ethernet frame. It goes into the radio encapsulates that entire Ethernet frame into a wireless frame. It then pushes the wireless, it encrypts it, it pushes the wireless frame wirelessly across the link to the other side. The other side decrypts it, strips off the wireless headers, and what I'm left with is the original Ethernet packet that came out of the camera, which then gets passed on to the rest of the network. So from the perspective of both sides of those links, it looks like I have a wire connecting those 2 points, when in reality I have 1 or maybe even multiple radios actually interconnecting those 2 points. Now with LigoWave, we support this is typically called a wireless distribution system. And there's a standard for this that a lot of vendors support. That's called WDS for wireless distribution system. LigoWave also has a proprietary protocol called iPole, which eliminates a lot of the wireless overhead that's common in WDS, and we can typically get 30% or better data throughputs over kind of the standard protocol, and I'll show you some examples of that. And this iPole protocol is available in all of our point-to-point and point-to-multipoint lines. So once you understand your requirements, you can actually start going through the process of design and figuring out, okay, you know, how this is actually going to look. And what you need to keep in mind when you're doing design is what are the things that you actually have control over in the design. So the first thing I have control over in any type of wireless design, especially wireless surveillance, is what kind of AP model am I picking? So what vendor am I going with? What model am I picking? And what type of antenna am I using with that? Now, many APs have antennas built in, and that's actually part of the attractiveness of them, is that you can get the small form factors by building in patch antennas into the access points. But if you're selecting that model of AP, then you are intrinsically choosing that antenna that comes with that AP. There are also AP models that I will show later that have external antenna ports, and you can hang your own antenna on it from a third party, which gives you more flexibility in terms of precisely the antenna pattern that you want to use, but typically adds more cost because now I have this extra component that I have to add to the network. But this is a degree of freedom that you have. I can pick which AP model and which antenna that I'm using for that link. I can pick the location. You know, where is it going, right? Subject, obviously, to the constraints of what my mounting options are. I can pick the transmit power, which is how loudly that radio is transmitting. And I can also pick the channel. So on what channel that radio is going to be broadcasting on. And when we talk about especially 5 gigahertz and 802.11ac links, you can basically pick channels all the way up from our equipment goes all the way down to 5 megahertz channels, all the way up to 80 megahertz channels. So, and there's some trade-offs there in terms of what kind of channel size that you want to pick, which we'll talk about a little bit later in the presentation. But these are the degrees of freedom that you have. Now, I should note that these design parameters are not independent. And hence, if you change one, I might have to go back and look at some of the other choices that I made. So if I'm going to, for example, pick a different AP with a different antenna, that might influence where I need to put it. It might influence what transmit power settings that I use and what channel settings that I use. So this is an iterative process, so keep that in mind. So now I'm going to walk through those 4 degrees of freedom. So let's start talking about how you actually pick the AP model and AP antenna. So the types of things that you want to look at, again, are your requirements. So what are the distances of the links that you need to establish? Are they short? And by short, you know, typically we're talking about, you know, 1,000 feet or 300 meters, which is very common in surveillance applications where, you know, the link distances maybe are only a couple of hundred feet or a few hundred feet. But sometimes you have applications where they're longer, and a lot of that will depend on your mounting constraints, how much area that you have to cover, and so forth. If they're long distance links, so if they're going to be links that are well over a mile or, you know, 1.5 kilometers, then you might want to be selecting different types of hardware than you would necessarily for short distance links. What kind of area of coverage do you need? So this will depend on where you need the cameras. And is it one link? You know, am I doing a point-to-point link versus am I doing a point-to-multipoint link where I have one point and multiple endpoints? Do I need to do relay shots? So do I need to go from A to B, B to C, and C to D? Or can I see everything directly? Also, what kind of outdoor rating? So is this going in a kind of a normal outdoor environment where, yes, I'll have weather, but, you know, it's not going to be anything extreme, versus I'm putting this on a saltwater beach, or I'm putting this, you know, in the Arizona desert in the summertime where the temperatures are going to get up to, you know, 150 degrees or, you know, 40, 50 degrees Celsius. So, which would require kind of a better outdoor rating. So depending on where you're going to deploy this network, what the environment is that this network is going to be operating under, will also influence the type of hardware that you want to select in order to make sure that it's robust enough for the environment that you're putting it in. I also have to look at the capacity, which is what's the total amount of data that I need to push over this network, and what kind of reliability do I need out of that. The core message here is that it's not necessarily one size fits all, which is why LigoWave and other vendors offer several different models of access points that are specifically designed for point-to-point and point-to-multipoint applications like wireless surveillance. So it's very important that you pick the right AP model for the particular application. And what we try to do, which you'll see in a few minutes, is that we have a couple of families of products that allow you to use basically standard components that have differences, for example, in the antennas that allow you to mix and match based on the particulars of your application. So I'm going to start talking about the long-range links. So these would be for links if you're going more than about 1.5 kilometers or about a mile. We have our LiGo Point-to-Point, LiGo Point-to-Multipoint rapid fire series, which is for long-range point-to-point and point-to-multipoint applications. We have multiple frequency options, including 4.9 gigahertz, 5 gigahertz, and we're also now launching 6 gigahertz, and we will have a licensed 6 gigahertz product in the US. In other parts of the world, we also have, where 6 gigahertz is unlicensed, we also have some additional options for doing 6 gigahertz in the unlicensed band. This series has single site configuration. It's got QoS in both hardware and software, and it uses our proprietary protocol, which I'll talk about in a few slides, which is really optimized for point-to-point and point-to-multipoint performance. And this is our flagship product. So in terms of the products that we offer, on the point-to-point side, we have basically two models. One has an internal 23 dBi antenna. The other has external antenna ports if you want to put on an even higher gain antenna. In the point-to-multipoint line, we have, again, we have a couple of base stations as well as some subscribers. So the base stations are your points, and again, they come in a 90-degree sector model or a model with external antenna ports. And then for our subscriber units, we have two internal models. We have a 20 dBi model and a 23 dBi model. And then if you need something higher or you need to use omnidirectional antennas for some reason, you can go with our external antenna models. Now, all of these basically run the same software, and they're all configured the same way. So the differences, say between the different subscriber modules, the only difference in how there's no difference in the software. The only difference is in the antenna that you're using. So to give you some perspective of why you might want to use external antennas versus internal antennas, you're typically going to be using external antennas for very long distance links. So this is, for example, for our point-to-point. This shows you how throughput essentially falls off as a function of the distance that you need to travel. The top line on the x-axis is kilometers, and in parentheses underneath it is miles, to give you some perspective of scale. And the vertical axis is the maximum data rate in megabits per second. As you can see, the red line is using the internal antenna, the 23 dBi antenna. If you use a 30 dBi external dish antenna, you can obviously get longer distances because the antenna basically serves to focus the signal in a particular direction. And so the higher the gain of the antenna, the more narrowly focused the beam and the further the distance that you can travel, which means that I can achieve the same speeds at further distances using external antennas. To give you a somewhat extreme example, this was an application that we did about a year ago. It was a 190 mile or 300 kilometer point-to-point link from Rome to Sardinia. And you can see we have like a 4-foot external dish antenna on here. And we could still get throughputs of over 100 megabits per second and got decent RSSIs in the neg 60 to neg 70 dBm range. So, even for very, very long distances, you can use this type of equipment. This is an example of a Point-to-Multipoint application using the enterprise-grade Point-to-Multipoint gear, which was a municipal surveillance project. The city here was putting cameras on traffic light poles to keep an eye on traffic and traffic patterns and people who were running red lights and so forth. Their NVR was in their police station, which was in that corner of the top right corner of the town. And they had 5 links to start, and we did this with a single LiGo base with an integrated 90-degree sector antenna. And we had 5 subscriber units, each one located at various traffic intersections, and then the cameras were wired into that. So and the maximum distances here were about 1.5 miles. And they had roughly 2 to 3 cameras per location. Now, for many surveillance applications, you're really going to be looking at shorter to mid-range wireless links. So, I would say probably 90 to 95% of surveillance links are typically in the 1,000-foot or less range. So this is what we recommend our LigoDeal Beeline for. It's less expensive. You're using plastic enclosures as opposed to metal enclosures. And this is our much more kind of cost-effective line and is very, very good for doing these kinds of short to mid-range links. We have these available in both 2.4 and 5 gigahertz, and outside the US in regions where 6 gigahertz is unlicensed. We have launched these products also in the 6 gigahertz band. All of these products are IP65 or better, and our enclosures don't turn yellow, unlike some other vendors I won't mention. The nice thing about these access points is that they're small, they're light, but they have still all of those enterprise level features that we talked about included. We have an integrated spectrum analyzer, we have integrated surge protection, we have integrated the IPOL protocol, so we can get the throughputs typically on a 5 gigahertz AC 2x2 link. From most vendors, the maximum throughput you're going to get is around 300 to 350 megabits per second. We can get around 500 megabits per second with this equipment under those same conditions. But we're also backward compatible, so if you wanted to run in the standard mode for whatever reason, say you were rolling out our equipment on an existing network and replacing things piecemeal, you could run it that way. We generally don't recommend it because you won't get the speed benefits without using our protocol, but we have that capability built in here. The 2 models that I want to kind of feature are our DLB590 AC, which is a new product. It's an integrated 90-degree sector antenna with an 18 dBi. And then our DLB520, which would be used at, so that would be used at the base. And then at the endpoints, you would use either the DLB515 or the DLB520 AC. And those have internal patch antennas of 15 and 20 dBi, respectively. And all of those are at IP66. We also have a model that has external end connectors for doing, if you needed an omnidirectional antenna, let's say, at your base. So let's say I was had a building and I needed 360-degree view without too many cameras. I could just put the DLB5 AC there with omnidirectional antennas, and then have the DLB515s or 520 pointed back to that. Now, one of the things that we have coming out, it'll probably be late this quarter or early next quarter, is the 515 AC Dual. So this is a product that's based on the 515 AC, but it is specifically designed for outdoor surveillance. It's a dual port outdoor point-to-multipoint product, and it uses standard IEEE 802.3 AF/AT as an input and has PUE pass-through, which means that you could plug in a camera directly into it without needing a separate injector for the camera. So we'll expect to see that around the end of this quarter, beginning of next quarter. Around the same time, we're also going to be introducing an industrial grade switch for outdoor applications. So if you need to extend, say I need to hang 3 or 4 cameras at a location, we will now have a switch in the series where you can actually, it'll have 4 PoE ports. It'll have either 1 or 2 SFP ports. It'll have a DIN rail for pole mounting and such. And there will be an option for a 12-volt power input. So if you're doing solar panel, if you're doing a solar panel at a remote pole, typically the output is 12 volts DC out of the solar panel array, and you can power this directly out of the solar panel without needing additional converters. And again, this will also be arriving probably early Q4. You know, typical kind of surveillance layout is, you know, I'd have my base station, which would be my 590s. I'd have a series of different endpoints for point-to-multipoint, and I could have 1, or I might have several cameras plugged in at each endpoint. And one of the nice things about our protocol is that we dynamically adjust based on the loading. So our protocol is TDMA based, but here in this example, you can see I've got that link in the middle has 3 cameras on it, where the 2 on the ends each have 1 camera. Our system will dynamically adjust based on the bandwidth demand so that that center link gets more of the airtime, so that it can actually, because it has more data to transmit. In terms of mounting, the 515 versus the 520 and the 590 has a similar mount to the 520. The 515 has a standard pole mount, and it comes with a hose clamp and for mounting on a pole, but that only gives you kind of a horizontal tilt control based on how you mount it on the pole. Our 520 AC and 590 AC have an innovative angular pole mount that allows you to actually control the tilt both horizontally and vertically, which is very, very convenient when you have applications where not all of your links are at the same level. So typically, for example, you may be mounting the base station on the roof of a building, and so that might be 3 or 4 stories high. And I may be mounting my cameras on poles, which are maybe only 15 or 20 feet high. So you have a height difference. So I need to be shooting down from the rooftop and then back up from the pole to the rooftop. That angular mount is really, really useful for being able to control the angle of direction so that you're pointed straight back where you need to be. We also sell optional wall mount brackets. So as I mentioned, right, if I'm mounting this on the side of a building or on a wall, we basically have some optional accessories that basically will turn the pole mount into a wall mount. Now, one of the frustrating things about design is, where do I actually put these links? Because you can't always get line of sight. So for the example on the left, this is showing you the ideal line of sight. So this was a surveillance project at a residential property, and when they originally came to us with the project, they said, oh yeah, the MDF is in the main building, and the main building is a story taller than all the other surrounding buildings, and you got line of sight to everything. So we did an initial design based on, okay, I've got line of sight to everything, and the different color groups are basically showing you the different point-to-multipoint links that we were using in order to have sufficient capacity to handle bandwidth from these 32 cameras. But it assumes that I could actually have RF line of sight to all the locations, that I can see all of those locations. The reality on the ground, though, was very different because it turned out that no, the MDF was a 1-story building, and some of the surrounding residential buildings were actually 2-story buildings. So I can't just shoot through the buildings. So we needed to pick paths that actually allowed us to go around the buildings or through or between the buildings or follow the roadways, so that we had clear line of sight to various locations. Now, fortunately, this didn't actually add too many additional access points. Here we only wound up adding another 6 access points, which is roughly 20% here. But you can see the design is much more complicated, and in many areas I've got much longer links, and I have to do upwards of 3 hops to a location. Typically, when I do a wireless surveillance design, I try to keep it to 3 hops or less, because every wireless hop will introduce latency, and as everybody who has done any type of video surveillance application knows, latency is your enemy. And those latency errors stack linearly, and it's just the way that wireless works, is that there's a certain amount of lag between when the signal gets transmitted and when the signal gets received. So you want to minimize the latency as much as possible, especially for higher resolution cameras. So you want to try to minimize the number of hops that you need to take. Most applications, you can generally figure out a way of doing it in 3 or less. And in this case here, you know, you can see that generally the red dots on the map are showing where the cameras are located. Generally, I'm going to pick relay locations where I have to put cameras anyway. So because I'm already going into that building and I'm already mounting equipment there. So to mount some additional equipment there is not as big a deal. And so you try to pick relay shots for areas that you need to pick anyway. Now, keep in mind when you're doing this type of design that you need to actually be concerned about the bandwidth on some of those initial links. So for example, if I look at the blue link over here, I don't know if you guys can see my mouse, but if I look at the blue link over here, right, off of the blue link, I've got, you know, some green links and I've got some orange links for some secondary links. Keep in mind that all of that traffic, right, from those secondary and even tertiary links will come back and stack up, and so on that first set of link, I've got all of that camera traffic coming out over that link. So when you're planning these out, you need to make sure that you're not exceeding the bandwidth capacity of any of your links. Typically what that means is I'm going to try to get as many shots as possible out of the MDF. In this particular example, I've actually got 5 different links, excuse me, coming out of the MDF pointed in different directions. In order to balance the load so that I don't have too many cameras coming across any individual group of links. When we're doing, you know, when you're in the business of doing wireless surveillance and I'm doing multiple properties, then obviously what you want to do is, you know, I don't want each project to, you know, be using a different set of equipment and a different set of hardware, because somebody has to go and maintain these things over time. So we want to follow a process of mass customization. And by mass customization, I mean that I have standard components in the toolbox. So I've got a standard set of APs that I use, and then I will tailor which APs I'm going to use based on the specific needs of a property. So in this example, this is a bit smaller than the last example that I showed. We had 9 camera locations, which are represented by the yellow push pins. And we had the NVR was actually in the middle of the property. I can't tell you how many properties I've worked on where the clubhouse or the NVR is located in one corner, which always makes it that much more challenging. So we like it when the NVR is actually located reasonably close to the middle of the property. But again, I don't have line of sight, and you can see cam 1 in the upper left-hand corner, there are just too many buildings and trees in the way, and I actually needed to do a relay shot on a light pole in order to basically follow the roadway in order to get up there. Now, you'll notice that both of those links are in purple, and we've reversed the flow of the point to multipoint. So typically, when we do a point to multipoint, the point is upstream, right? So it's closer to the NVR, and the multipoints are downstream, which are, you know, closer to the endpoints where the cameras are located. However, the equipment doesn't care about the direction of traffic flow. As I mentioned before, it will dynamically adjust to the application in which way the information wants to flow. And in this case, along the purple link, right, pretty much all of your video traffic is flowing from cam 1 to that light pole and then out again towards cam 3. So then it can then take a secondary link back to your main distribution frame where your network video recorder is located. And that's perfectly fine. And that saves you some additional equipment and having to worry about additional links. So in this particular case, we had 9 cameras, and we were able to do this with a total of 16 access points. So using one of those 590s, and everything else, we use just the standard 515 AC. Another very interesting application for surveillance is doing elevators. So modern elevators are typically built with a rolling Cat 5e cable to provide network connectivity inside the elevator cab itself. But typically in older buildings and older elevators, they don't have such wiring, and putting in such wiring can be very, very expensive. But this is also a very good application for doing wirelessly, because the wireless link will actually adjust as the elevator cab moves up and down the elevator shaft. Obviously, the length of your link is changing, but that's fine, and the link will dynamically adjust for the fact that it's actually moving over the course of time. So you have one link in your elevator cab that's hooked up to a camera or any other network devices that are in your elevator. You can then put the DLB on the roof of the elevator, and then you put a second DLB at the top of the elevator shaft to communicate with the elevator cabs in the shaft. Now, this is shown for point to point, but you can actually do this point to multipoint, where each elevator cab has basically its own, right? It's an endpoint, so each one has its own radio, and I just have one radio centered in the middle of the shaft at the top. One of the things that makes this particular application challenging is that it's an elevator shaft, which means that it's basically a big steel box. So you get a lot of signal reflectivity and so forth. So you get a lot of multipath being generated. But the equipment is actually very good at handling that. So you would do this in a point-to-multipoint scenario, and then the links are dynamically adjusting based on whatever floor that each individual elevator is on. So I want to have a note here about transmit power, because I mentioned that was one of your degrees of freedom. Typically, the higher the transmit power, right, the louder that the radio is speaking, which means the greater the distance that you can transmit. Now, when you're doing point to point, you typically want to match the output power of both sides of the link, and you typically want to match the output power that you need to whatever the link distance is that you're using, and whatever antennas that you're using. Remember, the antennas are also serving to focus the beam in a particular direction. So the higher gain the antenna, the longer the signal will travel at the same transmit power. So you can, again, these are two knobs that you can turn, right? What's the gain of the antenna versus the transmit power? Keep in mind that there's some differences, because the antenna basically acts like a lens. So it enhances both your ability to talk in a particular direction as well as your ability to hear in that direction. Whereas transmit power is just the volume of your voice. So it's only affects the ability, your ability to talk, and has no impact on your ability to listen or to hear. So typically you want to try to get the antennas right first, because the antennas will work with you in both directions, whereas the transmit power really only allows you to tweak in one direction. Now, typically you want to target your RSSI to be in the -40 to -50 dBm range. This is in order to be able to achieve the fastest speeds possible out of the hardware. As your links get longer, even with high gain antennas and so forth, that target may not necessarily be realizable. You're typically going to want your links to be above an RSSI of -70 dBm. So have them in the -60 to -70 dBm range for long distance links, in order to be able to maintain a stable connection with a reasonable throughput. If you're doing very short links, so let's say I'm shooting to a pole that's 20 feet away, and I'm using these really big high gain antennas, you can actually run the risk of the links being too loud. So that they're literally shouting at each other. And that would typically be if your RSSI, which is your received signal strength indicator, is higher than about -35 dBm or so. And in that case, it's like shouting in somebody's ear. You're actually overloading the amplifiers and saturating them. And you can actually degrade your throughput because you're actually basically talking too loudly. So our links have a feature called automatic transmit power control, ATPC. You'll see that in the GUI. And you generally want to let the links, you generally want to turn that on for most applications, and let the hardware dynamically adjust the power level so that the RSSI is well loaded. In a point-to-multipoint scenario, though, where if I have links at very different distances, so say I have a link that's really close by and a link that's really far away, you may actually want to turn that off and actually tweak the power levels of each AP independently to match the fact that there are different distances. So now let's talk about picking the right channel. So typically when we're talking about wireless surveillance, most applications these days we're doing 5 gigahertz 802.11ac. The 5 gigahertz band has a total of 660 megahertz available. However, 2/3 of it are in the Uni 2 and Uni 2E bands, which are your so-called DFS channels. And these have rules in terms of where you can use them because of existing weather radar and other radar systems that are present. Also, depending on your regulatory domain, some of these channels may or may not be available in certain regulatory domains. So you need to really understand what channels are available to you in the regulatory domain that you have before you start picking channels. Now, I mentioned before, right, that there are different channel widths that you can pick. The wider the channel width, obviously the more data that you can stuff into the channel at any one period of time, which means the higher the potential throughput. However, you increase the noise floor as you increase the width of the channel, and you subject yourself to more sources of interference from the outside environment. So the general best practice is to select the smallest channel size that you actually need for the throughput that you have to have. So as I mentioned before, for example, our DLB series can get upwards of 500 megabits per second under ideal conditions using an 80 megahertz channel. If I'm only connecting 1 or 2 cameras, and so the bandwidth is 10 to 20 megabits per second, I don't need to have the link operating at 500 megabits per second. I could actually turn that channel width down to 40 or 20 or even lower to kind of shrink the channel size, which will give me a better noise floor. It'll give me more robustness to interference, and it will shrink the total capacity of the link. Again, though, if you only have a couple of cameras on the other end of that link, I don't need all that capacity. So you really want to match the channel size to the capacity that you're passing, which is why it's important to understand how many cameras are coming through that link. And when you're doing those multiple relay hops, you may, for example, be using 10 or 20 megahertz channels at the endpoints because I'm only going out to a handful of cameras at the endpoints. But as those are getting aggregated and then passed over links back to the MDF, those aggregated links that you're using, those might be at 40 and 80 megahertz channels because you're collecting the bandwidth of all of those cameras. So, at the point where I've got 9, 10, 12, 15 cameras shooting out over one link, you're probably going to be wanting to be using larger channels. So you can set the channel width based on how much data that you're expecting over that link. We have auto channel on all of our access points, so the APs will try by default to pick the best channel available. So it'll do an analysis of the other wireless networks. It'll do a scan of other wireless networks in the area and try to pick the quietest channel. However, if you're doing multi-link deployments, like I showed you before, where say I have that MDF and I've got 4 or 5 links coming out of that MDF, going in various different directions, you really want to have control over your own channels and avoid self-interference by actually setting those channels statically. Now, one of the trends that we're seeing in wireless surveillance is beginning to shift to alternate frequencies. And that's mainly because the reason that everybody went to 5 gigahertz was because 2.4 gigahertz was saturated with Wi-Fi. Well, guess what? Now 5 gigahertz is also now saturated with Wi-Fi. So there's a lot of interest in some new alternative frequencies, including 6 gigahertz, as I mentioned. It's unregulated in parts of the world. In the United States, it's actually being evaluated for unlicensed use, but currently it is a licensed frequency band, specifically intended for long-distance links. But we are releasing a product in Q3 that will be introduced as a licensed product for doing licensed 6 gigahertz links. In other parts of the world where it's unlicensed, we also have 6 gigahertz products available in the DLB series, and those can readily be used for wireless surveillance. We're also working on a 60 gigahertz product. Now, the nice thing about 60 gigahertz is that there's lots of bandwidth available, and they use 2 gigahertz channels, so the amount of bandwidth that you could push over those links is very, very high. It's well over a gigabit. However, at 60 gigahertz, you actually have to start worrying about things like rain and fog and snow, because those will actually serve to attenuate the link. Right at 5 gigahertz, I can ignore weather effects from water, but at 60 gigahertz, I can't. But you will see these kinds of products from us probably in very early 2019. And we're looking at using these in wireless surveillance as well, not so much because I need the huge amounts of bandwidth, but because they're very effective over short distances. And they will be, they won't be polluted by, what's going on externally from Wi-Fi networks. So enjoy the silence of these alternate frequencies as they start becoming available. So let's talk a little bit about some of the distinguishing technologies that LigoWave has specifically for wireless surveillance. So I mentioned earlier we have this proprietary protocol that's optimized for point-to-multipoint. It is a TDMA-based protocol, but it's designed to maximize bandwidth and minimize latency for point-to-point and point-to-multipoint applications. The way that conventional wireless works is that everybody shouts to talk, so it's like dinner at my house. But the way that WJetV and iPol work for point-to-multipoint is that everything is done via sequential polling. So the base station basically allocates to each endpoint when they're allowed to talk, when they're allowed to use the airtime, and goes around and dynamically adjusts based on client loads. So if different clients have different loads, it will allocate more time to the clients that have more loads versus others, and so it eliminates all of that contention and so forth, and it allows the subscribers to basically each have their own turn to talk at specific time slots. We have integrated QoS mechanisms and advanced multicast handling, and this allows us to nicely handle video and voice streams. And as I mentioned, the algorithm is self-optimizing, so it will dynamically adjust both for capacity, and you can have it dynamically adjust for both channel and transmit power using that automated transmit power control I mentioned earlier. The nice thing about this protocol is that it meets our need for speed, so we get over 30% faster data throughputs than you would using the conventional wireless distribution system that you would see in most other vendors. We also have recently introduced cloud management. We've had cloud management for a while for our Wi-Fi products. We now have cloud monitoring as well for our point-to-point and point-to-multipoint links, which means that you can monitor the state of all of your point-to-point and point-to-multipoint links from our cloud controller. And you can get alerts if a link goes down. You can look at statistics in terms of how much data is being passed over a particular amount of time. And we're also one of the only vendors that have both a public cloud and a private cloud option. So public cloud is usually popular with smaller integrators who don't have their own data centers and don't have the staff and don't want to worry about the overhead of maintaining their own servers. Private cloud is usually intended for larger customers who do have their own data centers and do have their own IT experts on hand and want to maintain it themselves. Now, the nice thing about having cloud management of the point-to-point and point-to-multipoint links is that you can actually surveil your surveillance networks, and you can keep an eye on all of your Wi-Fi and all of your point-to-point and point-to-multipoint networks from anywhere on any device. And another nice thing that you'll see about our cloud controller as well as the user interface on each of our products is that we have invested a lot of time in trying to make our interfaces easy and intuitive as possible. So the user interface is really designed with installers and integrators in mind and not software engineers. And we use the latest in HTML5 technology and responsive design to allow you to use these interfaces on any device. So I don't need to be dragging out my laptop. We have a lot of integrators that are only running around with tablets and in some cases even just smartphones and configuring devices straight from their smartphones. We also have an online tool called Linkcalc, which is a web-based tool. You need to sign up for an account, but the account is free. You just go to linkcalc.ligowave.com and you can just register and use it. And you can use this to plan all of your links. This is especially useful in planning long distance links, but it works just as well for both long distance and short distance. And it will take into account things like geography, the distance of the links, the antenna height, how high the antennas need to be. Especially for long distance links, you need to start worrying about the curvature of the earth. So it will account for that. It'll also account for antenna gain and the transmit powers. We're also adding to Linkcalc a camera bandwidth calculator, so you can put in information about you know, how many video streams, what the resolution is of the camera, you know, what kind of video quality you want, right? And so we can figure out essentially how much bandwidth we're expecting from the camera and how many cameras that you have. And then that will help you also determine if you have sufficient backhaul capacity within the links that you've designed, or if you need to add additional or readjust your design from a capacity standpoint. That's being, we have a beta of this available now. You'll see that integrated into our online Linkcalc very, very shortly, so that when you're doing wireless surveillance designs, you could use Linkcalc to not only tell you about the links themselves, but they'll also give you a sanity check to make sure that the links will have sufficient capacity. We also have an antenna alignment tool for Android platforms, which are useful primarily for long distance shots. It'll actually give you kind of a view of the horizon and where you need to point the antenna. So that's very useful when I don't have visual line of sight because it's too far away, but I still have radio frequency line of sight. So the radios can still see each other, but typically in those applications I'm using high gain antennas, and so I'm very sensitive in terms of, you know, the beam widths are narrow, so I have to make sure that the antennas on both sides of the link are pointed in the right direction. So this is a very useful tool for knowing how to aim your links, especially when I don't have direct line of sight to the other side. On board the access points themselves, we have a lot of diagnostic tools. So we can do a site survey, which will tell you about any other Wi-Fi networks that are in the area. We have a built-in antenna alignment tool. The APs do have the lights on the side of the AP for visual inspection, but if you want to fine-tune it, we do have an antenna alignment tool that will actually just show you what the RSSI is every second or two. So as you manipulate the position of, you know, the tilt of your link horizontally and vertically, it'll show you how the RSSI is increasing or decreasing, so that you can tweak your alignment. You can do a link test to actually do a throughput measurement from one radio to the other, and to indicate what the link quality is. We have in all of our products an integrated spectrum analyzer. So in addition to looking at just Wi-Fi, I can look at all of the RF in the spectrum, even if it's from non-Wi-Fi sources. So if I'm having issues with interference, we can do a spectrum analysis right from the access point itself, and that will tell you if there are sources of interference in the area and whether or not you should be moving to a different channel, as well as kind of the standard network diagnostics of ping and trace route. So our call to action, give us a try on your next surveillance project. We have free pre-sales engineering services. So if you need help in designing, you have a project and you need help in saying, hey, how many links do I need? Where do I need to put them? This is where I'm putting the cameras and so forth. You can bring that to us. We can run it through Linkcalc, and we can look at it in order to you know, advise you on, okay, here's the equipment that you should be using, and here's, you know, how many links that you need and what the appropriate channel and power settings are. So we can assist you with that design work if you need it. We do offer some demo equipment pricing. So if you want to, you know, just get a pair of links to try them out and kick the tires before you commit, we can arrange some demo pricing. We also have in-house phone and email customer support. So we do not outsource our customer support. So in the US, if you're call our support number, which you'll see on the next slide, you will actually get our offices in Canton, Georgia, outside Atlanta. We have a couple of social media contests going. The first is to show us your deployments. So for those of you who have erected or are in the process of putting LigoWave equipment out there, we want to see pictures. We want to post them on social media, and we'll be giving out prizes on a monthly basis to kind of who's got the sexiest deployment. And then for our 60 gigahertz product, we're going to be shortly announcing a naming contest where we're going to ask the community to help us name the product. And if we select your name as the name of the product, we're going to give you one of the first pairs off of the production line. So keep an eye out for that. We have lots of stuff on social media, Twitter, Facebook, Instagram, LinkedIn, and YouTube. We have a lot of resources on YouTube. We have a lot of how-to videos, you know, the little 4 or 5 minute videos to kind of show you, this is how you can configure a link. This is how you program X or Y. We have unboxing videos to show you what's in the box. We have training videos, and then we have webinars like this that also are on our YouTube channel. So please, you know, contact us, you know, give us a call, ask us questions, let us help you out with your next project. So with that, I see that a couple of questions have come in. So if you have questions, I know we're running a little short on time, but if you have questions, please post them into the question box, and I will go through them. Do you have a capacity table? So how many 2 megapixel sigma pixels are supported on the DLBN and DLBAC and LIGO PTMP series? The answer is yes, we have, and that's a table that I can share privately. As you can see, there are a lot of you know, knobs that go into this in terms of frame rate and video quality and so forth. But I do have my own little cheat sheet in terms of, okay, you know, how many cameras can I support over a typical, say, DLB AC link, you know, if they're 2 megapixels running at 20 frames per second, for instance. So we do have some charts that we can share with that you could use as an initial guide when you're doing some of your initial planning. However, we do recommend that you make sure that you're actually using tools like Linkcalc and actually calculating it specifically for your environment. But yes, we do have some capacity tables that you can use as an initial guideline. I see another question here about the differences between visual line of sight and RF line of sight that I made a reference to earlier. So within physics, there's something called the Fresnel zone, which is a zone around the visual line of sight that you need to keep clear in order for a signal to get through from one point to another. It tends to come into play on long distance links, but it can actually come into play even in short distance links if I'm shooting between buildings. And basically it means that, you know, if I want to shoot, say, over a rooftop, or if I need to shoot between 2 buildings, if I'm trying to do a grazing shot, so if I'm trying to basically shoot over a rooftop of an intermediate building to hit a building on the other side, if I'm right at the edge, that intermediate building is actually going to serve to deflect the signal off in the wrong direction, and that's a process called diffraction. And if you have too much diffraction, then obviously the signal essentially gets pointed the wrong way and doesn't go to where it needs to go. And typically, the way that you fix that is you typically raise the heights of the APs or the antennas in order to have a sufficient amount of clearance so that those diffraction doesn't really play a role. Okay, I'll leave it open for another couple of minutes to see if there are other questions. Let's see if there's anything in the... So please, if you have any other questions, please go ahead and post them now. Okay, well, we are at the top of the hour, so if you do have questions, I encourage you to contact us at support@ligowave.com or contact us on Twitter at LigoWave. You could also contact me on Twitter at Emperor Wi-Fi. and we'll be happy to answer your questions. And if you have any projects that you would like assistance with, please feel free to reach out and talk to us. So thank you very much, and I appreciate the time and the attention, and we'll see you soon on a future webinar.